Okay, now I would like to discuss the first step of the GW calculation, that is the generation of the wave function file, including empty states. This is the set of variables that are needed. So the idea is that, first of all, you perform a ground state self-consistent calculation with only occupied states plus some empty states, just to, let's say, make the SCF cycle more stable. And after this step, you get the density file. And from the density file, you know, in Cornish-Ham theory, you can construct the Hamiltonian and Cornish-Ham Hamiltonian, and you can compute the eigenstates and the eigenvalues of this Hamiltonian, including high energy states that are needed to build the polarizability of the self-energy. So the first line specifies the density file produced by the SCF cycle. This is just an option that tells Affinity that we want to compute Cornish-Ham eigenvalues non-self-consistently. This is the toll, the stopping criterion on the residuals of the wave function. This is the number of states that we want to compute. This example is for silicon, and obviously in silicon you usually have 4 occupied states, but here we ask for more states because we need to compute in terms of the sum over bands. This is a very important point, this parameter NBD buff, because the NSCF cycle will stop when all the states are converged within this stopping criterion. The problem is that high energy states require a lot of iterations, converge within stopping criterion. So with NBD buff, essentially what we are saying is that we don't want to check the stopping criterion for the last 120 bands. This corresponds to 10% of the initial number of states. So we are excluding the last states when we check for the stopping criterion, and we can save a lot of CPU time, because many applications of the Hamiltonian in the NSCF iteration are just needed to converge the high energy states that are unstable. So I would suggest to, let's say, use a very large number, usually 10% of N-band, to avoid problems when diagonalizing them, when computing the eigenstates for the GW calculation. The example I showed previously used the iterative techniques to apply the Cornish-Ham Hamiltonian. And for large system, what we usually do, we use the para-KGB option that corresponds to an optimized eigenvalue solver that is parallelized over K points, band, and FFT. Now here I have some tricks or some suggestions for the input parameters, but the main message is that if you use para-KGB1, you have an eigenvalue solver that is more scalable than the default one. And if you use AutoParal1, then Abinit will automatically select all the input variables related to the eigenvalue solver at runtime. So I strongly recommend using these two options in the generation of the wave function file. Then I would like
2 questions. First, regarding this buffer that you said, the first 120 you will compute and then extrapolate to.
No.
How is it this sort of the stochastic measure?
No. There's no stochastic. Essentially, what we're seeing. So this is the N-band. So here we have 1,200 states, and this is 10% NBD buff. When we compute the residual, that is in K, so the residual is defined by this equation. This quantity is always positive, is equal to 0 if and only if psi n k is an exact eigenstate of the Hamiltonian. And when the stopping criterion, we take the maximum over N and K of the residual. And this quantity should be smaller than tall W5.
Is 10 in order of minus 18
And yes, this is the typical value that we use for
residual.
But the stopping criteria is the maximum of N and K of the residuals should be smaller than tall W5, that in my example is 10 to the minus 18. Okay, but the maximum is done over all the bands and all the reports. Now what happens is that these are the high energy states, and the residual is usually peak. Says that after I don't know 10, 20 NSCF iterations, tall WFR for the low energy state will be already of the order of 10 to the minus 20. And here you start something of 10 to the minus 8 after 20 iterations. And you have to spend a lot of other iterations to bring this value down below 10 to the minus 18. So you're spending a lot of resources. And with the buffer and with the buff, you tell a bit, please, you need to bring these states when you take the maximum over bands. So the maximum is essentially done from 1 up to, and then the minus and be the buff. And then be the buff. So you're just taking the maximum in this region, and you're excluding the last states, and 10%. Does it make sense? Yeah. Okay, this is a new feature that is available in ABinit version 10. In a nutshell, you don't use these iterative eigenvalue solvers in which you have to apply the Hamiltonian many times. You just build the Hamiltonian in Fourier space, and then you use a scala pack to perform a direct diagonalization. And this is way more efficient when you have to compute a lot of states, and also has much better scalability. And this is a benchmark for zinc oxide that compares the work time needed by direct diagonalization versus iterative eigenvalue solver. So this is what I would recommend for your GW calculation when ABinit 10 will be released.
But it was already available at version 6.
But not with scala pack.
Not scala.
Not with scala. Okay. I lost connection. Okay, in the next slides, I would like to discuss the computation of the RPA polarizability in Fourier space. So this is the full polarizability, the reducible polarizability according to readings, where we have the vertex gamma. Now, as you know, in GW, gamma is replaced by a product of two delta functions. So in GW, polarizability is simply given by GG, and this corresponds to the RPA expression. So this is what you get if you work in real space, in frequency domain. In the time domain, it's just a product of two Green's function. By the convolution theorem, if you go to frequency space, you have to evaluate this convolution between two Green's function. If you use the lemma representation for G and you do the convolution, you can obtain an analytic expression, and it gives you this denominator. And this is the lemma representation in real space and in frequency domain, where mu is the chemical potential. And then we have this complex shift theta that is called Z, named Z cat in those values reported. This is needed to avoid the poles on the reactants. Now, if we express the Adler-Weiser expression in real space and the frequency domain along the real axis, we obtain this expression here. But in ABinit, as I mentioned, we work in Fourier space. So this means that we have to transform these two spatial variables to the Fourier in residual space. And after some math, what we obtain is the following expression here. As I mentioned, all our quantities are now given in terms of a big matrix that depends on two plane wave indices, wave vector Q in the first Brillouin zone, and frequency. Now, the number of plane waves in the polarizability is specified by IKTPS. These are the dimension of the energy, stands for the cutoff energy, for epsilon for the electric matrix. Here we have a sum over K points over the full Brillouin zone, and these K points cannot be changed at will. They depend on the K points used to generate the wave function file with the eigenvalues and the Kohn-Sham orbitals. Here we have a sum over conduction and balance. We are assuming a system with a gap. The number of let's say empty states that you want to include can be changed at this level in the input file by just playing with the n band, but clearly the number of bands cannot be greater than the number of states that are already available in the wave function file. Then, okay, if you want to sample the polarizability, then there are other variables defining the linear mesh along the real axis, or you can also sample along the imaginary axis. And these m matrix elements are essentially the matrix elements of a plane wave between two Kohn-Sham states, and these terms are computed with a fast Fourier transform instead of using this expression here in Fourier space directly that requires the evaluation of a convolution. And the mesh for the FFT, for the m matrix elements, is defined by FFT-GW. As I mentioned to you, when you have a product in real space, then in Fourier space, the cutoff energy is 4 times the cutoff energy for the wave function. So that there are options that allows you to select an FFT mesh that is large enough to treat this convolution, or an FFT box that is smaller, that is more efficient, but also introduces some numerical noise. This is an example of a typical input file for a screening calculation. First of all, we read the wave function file using this variable here, and this is the string defining the path to the external file. Optodriver 3 activates the computation of the polarizability. This is the cutoff energy, defining the number of plane waves in chi, and this is the number of bands in the RPA expression. Perhaps other things that is worth mentioning here. As I told you, the reports are tuned for plasmon pole approximations. In this case, you need to compute the polarizability at 1 or 2 frequencies. So by default, if you don't change the standard behavior, ability computes the polarizability at another point along the imaginary axis. And the PPM fact defines this frequency along the imaginary axis, and by default is set to the Drude plasma frequency. That depends on the number of valence electrons you have and the unit cell volume.
This plasma pole frequency is the dielectric. It's somehow, we had a discussion with Francesco that there is a peak in polarizability that this ppm actually is gonna be that number. How do you define this ppm, the frequency in dealing with? Yeah, my question is that how you usually select this frequency in the ppm method?
Okay, because I still have to discuss the plasmon pole approximation and how it works. But in this case, the idea is to compute the polarizability along the imaginary axis, okay, not along the real axis. Just because you want to have a model that can be generalized to the complex plane and you want to reproduce some ab initio results, you move along the imaginary axis because the polarizability is smooth. So your fit is more stable. Yes. So this is not the real plasmon frequency that is along the real axis. But you don't want to move along the real axis because you're going to have a lot of oscillations. Okay, so according to our test, using this second point for the plasmon pole fit, let's call it like this, and set it to the Drude plasma frequency is a good idea because you still have something that has structure but is, let's say, not too high in frequency, and so the fit is numerically stable. Okay. Another point that I would like to mention is that at the level of the quasi-particle gap or quasi-particle energies, there's a cross-convergence in the sense that the results depend on the number of plane waves that you introduce in the polarizability as well as the number of bands. The reason is that if you go to a large G, these large G components are very sensitive to the contribution given by high energy states. So this means that you cannot simply perform a one-dimensional convergence study, but you have to increase the number of empty states and the cutoff energy at the same time, as shown here, because obviously if you fix one parameter, for instance, TPS, and then you move, you increase in band, and then you find the converged value here. If you move along the other axis, obviously we find another value here. But as you can see, the most reliable approach would be to converge both in band and TPS, and this is the kind of convergence value that you should get at the end. Another point that I would like to mention also that we found that this kind of cross-convergence study can be done at a relatively small K-point sampling. So you can start with the gamma oleo or 222, perform this kind of analysis to find the optimal value of the band and the TPS, and then you start to increase the K-point sampling. Okay, very briefly, as I mentioned, the code is able to exploit symmetries for the wave functions, and the similar trick can be used for the polarizability of the self-energy. So the polarizability is a full invariant if we rotate both arguments, spatial arguments, and here we have the spatial rotation, the fractional translation. If you start from this equation and you go to Fourier space, then you get a relation from the polarizability at point RQ and the polarizability at point Q. This is the expression that we use to reduce everything to the IBZ. So in other words, we don't need to compute the polarizability for all the Q points. We just consider the Q points in the IBZ, and then we use this kind of symmetry properties to reconstruct everything in the full Kelvin zone when needed. Okay, so these are the equations required to compute the screen interaction from the polarizability. This expression can be equivalently rewritten in terms of the inverse kinetic matrix that is given by this expression in matrix notation. So the idea essentially is to, once you have the polarizability chi, you build the dielectric matrix epsilon, but we need to invert this matrix, and this is done, let's say, in the Fourier space, frequency domain. And once we have the inverse dielectric matrix, this is the quantity that we store in an external file. So here we are inside of driver 3, the calculation of the polarizability that ends with this step, this matrix inversion, and then the results are written to file. Another point that I would like to mention is that in semiconductors, the head and the wings, the head refer to the 0,0 component, and the wings refer to the G0 or the 0G component. They tend to 0 in the long wavelength limit. When we compute epsilon, we have to multiply chi tilde by the Berg-Coulomb interaction. So in principle, we have an ill-defined form, 0/0 form. But this expression is finite in the long wavelength limit. The problem is that from the point of view of the implementation, we have to compute the limit of these matrix elements from full tending to 0. And if you do some algebra, you can express the matrix elements of the position operator that are ill-defined when you enforce periodic boundary condition. You can express this operator in terms of the commutator between the conventional Hamiltonian and the position operator. So now there's a lot of algebra involved, but the main result is that these matrix elements can be expressed in terms of the commutator of the Hamiltonian. And since we are using epsilon potentials, there's an additional term coming from the non-local part of the pseudo. This part is expensive, but it's very important, especially if you are interested in optical properties. You have a few points, one isotropic system. And you will see that a similar input variable is also used in DP and the EXE for the beta sub-beta. So by default, we always compute this additional term. If you want to disable it, then you set include VTB to 0. The calculation are faster, but obviously you introduce an approximation. In this slide, I'm essentially mentioning that if you want to compute the polarizability for several frequencies, then there's another technique whose computational cost does not scale with the number of frequencies that you want to compute. This is the so-called Hilbert transform, and is mentioned in this tutorial. And this technique is inspired to a similar method implemented in BASP. This is what I would recommend if you want to go beyond the plasmon pole. So we will see that in the plasmon pole, one frequency or two frequencies are enough to compute the self-energy. If you want to evaluate the convolution numerically, you have to compute the polarizability for several frequencies, and in this case, I would suggest to use the Hilbert transform method. Okay, this is an example, but you will find a similar input file also in the tutorial. And now I would like to discuss the computation of the GW self-energy and the quasi-particle corrections. So this is Eadin self-energy with the vertex, and we are that gamma is equal to 2 delta functions, and this is the GW expression. Okay, we have already seen the physical interpretation of the self-energy, and in particular the Dyson equation that connects the Kohn-Sham mean field Green's function G naught to the fully interacting G. Now, we never construct G or sigma explicitly as a function of R prime, and omega, but what we do, we solve the so-called quasi-particle equation, in which we have the first term that is essentially the RT Hamiltonian plus this integral in which sigma acts as a kernel. But I would like to mention that here the self-energy must be evaluated at the quasi-particle energy. So this is not a standard eigenvalue problem. This is a non-linear eigenvalue problem because our unknown quasi-particle energy appears on both terms of this equation. The quasi-particle energies might be complex. So the real part is the position of the spectral function. The imaginary part gives you the lifetime of the excitation due to electron-electron interaction. Now, if we compare the quasi-particle equation written here with the Kohn-Sham one, obviously the first two terms are R3 plus external potential. The main difference is essentially that in Kohn-Sham we have a VXC. In the quasi-particle we have this integral in which sigma acts as a kernel. So from this perspective, we can see VXC as a static and a local approximation to the self-energy. But we have already solved this problem at the Kohn-Sham level. So this means that we can reuse this information to try to solve in a perturbative way the quasi-particle problem. Now, the main assumption is that we assume that the quasi-particle amplitudes of the quasi-particle orbitals are equal to the Kohn-Sham. And under this assumption, if after some math, what you get is that the quasi-particle energy, the solution of this problem here, can be written as Kohn-Sham plus a correction term. But again, this correction term contains the quasi-particle energy inside the self-energy. So this is a nonlinear problem. In principle, we can solve it, provided that we know the frequency dependence of the self-energy along the real axis, but this is expensive. And usually the quasi-particle energies can be seen as a small correction to the Kohn-Sham. It depends on the system, but in the, let's say, simple SP materials, usually the corrections are relatively small. So this suggests to expand the self-energy using a Taylor expansion around the Kohn-Sham. So we assume that the correction is small. So we expanded the self-energy here using this standard Taylor expansion. And we introduce also the so-called renormalization factor that depends on the derivative of the self-energy with respect to omega. And under this assumption, the so-called linearized quasi-particle, we obtain that the quasi-particle energy is equal to the Cornish-Sham plus this term here, in which the self-energy is evaluated at the Cornish-Sham level, and we know the Cornish-Sham energy, so we don't have to solve the linear and the self-consistent quasi-particle energy. And this term here then gets multiplied by the renormalization factor. And if you do the math, what you realize is that this Z is essentially the area associated to the quasi-particle peak. So this means that if G is greater than 0.7 or is around 1, means that you have a well-defined quasi-particle peak. A value of G smaller than 0.7 means that there's some additional structure due to the satellite, because as you know, the spectral function integrates to 1. Now, how do we compute the self-energy? Okay, as I mentioned, the time domain is just a product of G and W. In the frequency domain, we have this convolution. Now, we split the spin interaction in two terms by just, let's say, adding and removing the Bercoulomb term. So the W can be written as a first term that is just the Bercoulomb interaction that is long-ranged, plus what we call WC, the spin part of W, that is a short range. It comes from this inverse electric matrix -1. And if you use this, the composition of W, the self-energy, and you do the math, you can compute the convolution introduced by V, easy, and this gives you the Fock operator. We call it the sigma X, exchange part, that is a static and emission. And then we have the correlated part, that is frequency dependent and non-emissions. Now, another important point that I would like to mention is that we never compute the self-energy in real space or as a function of GG prime. We computed the matrix elements of the self-energy in the Cornish-Sham basis set. And if we're interested in one shot, we can solve the linearized quasi-particle equation. We don't need all the off-diagonal terms. We can just focus on the diagonal parts and only force the states around the gap. And this is the typical output that we obtain at the end of the calculation, which we have the key point for the self-energy here. And then, okay, the spin index, the Cornish-Sham gap, quasi-particle. And these columns are essentially the matrix elements of the VC, the exchange part, the correlation part evaluated the Cornish-Sham energy, the renormalization factor, and then you have the quasi-particle correction, the difference between the GW and the Cornish-Sham. As concerns the selection of the key points, you can select them explicitly in terms of these three variables that define now the number of key points that you want to include in the computation of sigma, and then the list of bands. Or you can let Abinit decide automatically these parameters, and usually we set QP range to 0 because we are mainly interested in the correction for the fundamental and the optical gap. So this is very handy if you don't want to specify all these parameters manually in the input file. As concerns the computation of the exchange path, we have that sigma X is simply given by G times P, and if you do the math, what you get is the Fock operator. The main difference is that is the Fock operator computed with Cornish-Sham functions. And if you express all these terms in Fourier space, this is what we get. And we have a sum over value states, 2 points in the full Brillouin zone, and another sum over G, and the number of G's is controlled by this variable. Now, this is the Bercoulomb interaction, converges slowly in G space, and one has to be careful because there's also a divergence when Q is equal to 0, and there are different techniques that you can use to accelerate the convergence with respect to the K-point sampling. And here, everything is documented on the Abinit website, but anyway, the main idea is that you have an integrable singularity when Q is tending to 0. So you add or remove a function. This function has the same divergence as the previous function, but is integrable. So numerically, we have to evaluate the self-energy in which part of the divergence has been removed. The Coulomb divergence for Q tending to 0 has been removed thanks to this function that is discussed in this paper here. This is the default behavior, but it's not necessarily the most, let's say, the most efficient one, because we found that one can also compute the integrals of the Coulomb interaction with the Monte Carlo techniques, and this usually leads to a much faster convergence with respect to the number of points that are not seen here, but okay, this is the number of key points or Q points, let's say, in the evaluation of the Fock operator. So by default, okay, we use this method here. For production, we usually activate the Monte Carlo technique, but everything is explained in the documentation. This is the expression for the correlated part. Okay, I don't know if you have realized that in the Fock operator we only sum over occupied states. So the exchange part is at the GW level is way faster than the correlated part, because in the correlated part we have again the sum over Q points in the full prevalence zone, a double sum of plane wave indices that enter here and matrix elements. And this the number of plane waves is defined by the cutoff in the polarizability. And most importantly, in the correlated part, we have to sum over an infinite principal infinite number of states, and the convergence is very small. It is very slow, sorry. Now, the problem is that this term here is frequency dependent, and the frequency dependence comes from this integral here. I'm not going to report because it's really a nightmare. There are a lot of terms. But the main point is that a lot of several techniques have been designed in order to evaluate this integral as a function of omega as fast as possible and with the reasonable accuracy. And there are, let's say, two techniques that are commonly used in this field. The first one is a plasmon pole model that is an approximation, but is fast and usually works nicely for states around the gap. And the other techniques rely on numerical integration of the convolution. But in this case, we need the polarizability as a function of omega, both along the real axis and the imaginary axis. So they are way more expensive than the plasmon pole, but they are also more accurate. So now I would like to discuss in more detail this plasmon pole stuff, because it's important and there are advantages and drawbacks. So the idea is to model the frequency dependence of epsilon minus 1. We have a model that allows us to obtain epsilon minus 1 everywhere along the real axis. So in the plasmon pole, what we assume is that the imaginary part of epsilon minus 1 is essentially a delta peak located at the plasmon resonance. Okay, this omega G1, G2 on Q, because we are working in a crystalline system, so our depend on two plane wave indices and a vector. And this is the strength of the plasmon resonance. Once you have this model, you can use Kramers-Kronig causal relation to obtain the real part from the imaginary part. And this is the model that we have. So if you assume that the imaginary part can be modeled with a single peak, then these are the parameters for the real part. But how do we obtain these parameters? So A, omega, and big omega. Omega is just a function of this A and omega. So in order to obtain these parameters, we fit ab initio results. So we try to reproduce ab initio results as close as possible. And okay, I'm going to skip these two models. I'm mainly focusing on these two techniques. This one is the plasmon pole by log units. That is the default model. In this case, we obtain these parameters in order to reproduce the ab initio values for the static limit and for epsilon minus 1 along the imaginary axis. Okay, we don't move along the real axis because we are going to have oscillations. The fit is not going to be stable. So this is sort of analytical integration. In this case, we need to compute the polarizability at two frequencies. And then there's another technique method proposed by Ebers and Louis. Unfortunately, I don't have the reference, but you will find it in the update website, in which the parameters are fitted in order to reproduce the static limit and the F-sum rule. Okay, this is the default, and this is what we would recommend as a rule of thumb. The second plasmon pole tends to overestimate to give results that are slightly larger than the first plasmon pole. Again, this is an approximation. Usually works well for states around the gap, but there are also some drawbacks that you should be aware of. So first of all, this is the typical error. When I say error, if we compare the results with the more expensive numerical integration, the self-energy, this is the typical error that we should expect for simple SP materials. If you have DOF and or metallic system, I will not recommend, say, the plasmon pole. But again, it's a very nice tool for initial convergence studies, and it's very efficient both in terms of the CPU and memory. But here there are drawbacks that I've already mentioned. So for DOF electrons, I would recommend the contour deformation. Most importantly, you cannot have access to the spectral function because you only have the delta peak, so you cannot study, let's say, the lights. And okay, this is a figure that shows the real part of the self-energy in aluminum calculated with and without plasmon pole. This is the Fermi level, and as you can see, the plasmon pole leads to a physical oscillation metallic system. Typical input file for self-energy calculation with the plasmon pole. In these two lines, we specify the path to the wave function file and the screening file containing the static limit and another point on the imaginary axis. This is the cutoff for epsilon when we build the self-energy. This is the cutoff for the exchange part. The number of bands that we are gonna include in the computation of the correlated part of the self-energy. And this section here specifies the key points and the bands for the fuzzy particle correction or for the matrix elements of the self-energy. So in this case, we are just computing the correction for one key point, gamma, for band 2, 3, and 4. Any question? Very quickly, if you want to go beyond the plasmon pole, this means that you have to compute a convolution between the G and W along the real axis. And in principle, this integral is from 0 up to infinity. So you have to sample many frequencies. And the problem is that both G and W, they have poles along the real axis. So you need a very high resolution in frequency space, and the numerical integration is tricky. So that's the reason why we avoid this integral from 0 to infinity, and we use basic results of complex calculus, Cauchy theorem, to rewrite the integral along the real axis in terms of an integral along this contour, in which we have to sample G and W along the imaginary axis. And in this case, the integral function is smooth because we are far from the poles that are located along the real axis. And then we have an additional term that comes from the residuals of the integrand inside the contour. But we know the position of these poles because we know the position of the G thanks to the Lemann's representation. Okay, to make a long story short, instead of sampling everything from 0 up to infinity, we only need to sample compute the screen interaction along the imaginary axis, the positive branch, and we need to compute the polarizability only for a restricted set of frequencies along the real axis, but we don't have to go up to infinity. Okay, and this is essentially the expression that you get for the correlated part of the self-energy in terms of an integral over the imaginary axis an integral coming from the poles inside this contour. But the poles are only limited to a finite frequency range. You don't have to go up to infinity when sampling the screen interaction. And these are the three parameters that allows you to select the frequency mesh in the polarizability along the real axis. Okay, well, if you use the contour deformation method, then you can also obtain the spectral function. By default, this calculation is deactivated because it's expensive. But if you want to do contour deformation plus spectral function, then you select the number of points in the input file. By default, is 0, and also the maximum frequency along the real axis. And this is what you should get. I think this was a result for silicon dioxide, something or spectral function. Reference aluminum. Okay, all the results are stored in a text file here, and then you can plot it with Matplotlib or with or any other tool. And as you can see here, we have the quasi-particle peak plus some satellite. Okay, so as I mentioned at the beginning, the code supports both non-conserving and the PW. Although I would recommend non-conserving pseudopotentials for your applications, but even if you use non-conserving pseudos, there are a couple of technical points that are worth mentioning, because a pseudopotential is essentially mimicking the interaction seen by the valence electrons due to the core electrons that are frozen and the nucleus. The pseudopotential is built in order to reproduce the wave functions outside a certain core radius and the eigenvalues of the energies in the isolated atom. We use pseudopotentials because the wave functions are smoother. We get rid of the Coulomb singularity around due to the interaction with the nucleus, so we need less plane waves to describe the interaction. We also get rid of our electrons, so we have less electrons that should be solved self-consistently. The problem is that the pseudopotentials cannot reproduce the nodal shape of the wave functions around the origin, the fact that the wave functions have oscillations in presence of the true interaction. And moreover, core electrons are frozen, so they do not relax self-consistently, okay, when we perform a calculation for a crystalline system. These are very well-known problems, limitation for Cornish-Sham and ground state theory. The problem is even worse when you go beyond Cornish-Sham, and in particular because we have the Fock operator exchange part. Because the Fock operator depends on the atomic orbitals. And when we take matrix elements, the nodal shape of the wave function is important in order to have accurate results. And in order to have accurate results, we should include in our pseudo the electrons that are supposed to give the most important contribution to the Fock operator. Now, this is an example for gallium, in which you can have different electronic configuration, what we call the core valence partitioning. I mean, you can have a version that contains the 3D electrons, then 4s and the 4p. This is shown here. These are the 3D states. And then we have 4s in the black curve, and the 4p is the red curve. The dashed one is the pseudized wave function, and the solid line is the all electron. As you can see, the pseudized one is nodeless, whereas the all electron has two nodes here. Now, in this this figure here shows also the logarithmic derivative that is a proxy for the scattering properties of the pseudopotential, in the sense that the pseudopotential should be able to reproduce the scattering properties of the all electron atom. So if the solid line here is reproduced by the dashed line that corresponds to the pseudo, we are confident that our pseudopotential is able to describe the scattering with electrons at this region here. The negative energy corresponds to bound states, and the positive energy corresponds to unbound states. For ground state application, it's very important to have a solid and dash lines that are on top of each other in this region. So if I look at this plot, what I see is that this pseudopotential has good scattering property for occupied states, but it fails to reproduce the scattering properties of the whole electron atom at high energy state. And this is important for GW application. And most importantly, the 3s and 3p states are not included in the pseudopotential. Now, it's very well known that this configuration is okay for ground state. And if you want to do structural relaxation, band structure, molecular dynamics, this pseudopotential is perfectly fine. But this is not what I would recommend for GW calculations. And the reason is seen here, in which I have another pseudo, in which now the 3s and 3p electrons are treated as valence. And you see these states here. So this red dash the line corresponds to the p, and the black curve is the 3s state. And as you can see, the 3s and 3p overlap with the 3d electrons. So this means that if you have a system in which the 3D electrons participate to the CPM or the VPM, then if you use this pseudopotential, the 3s and the 3p electrons will be included in the Fock operator in your self-energy calculation. And the matrix elements of sigma x will see this overlap. If on the other end, you use the pseudopotential, these 3D electrons won't see the exchange with the 3s and the 3p simply because these electrons are frozen in the pseudopotential. So, and this can have a huge impact on the matrix elements of the exchange part. And the last but not least, if you compare the logarithmic derivative obtained with by including 3s and 3p in valence, you see that now this the pseudopotential, let's say, is able to reproduce the scattering properties of the whole electron atom up to, let's say, 7 eV, whereas this other pseudopotential starts to fail at 5 arc, sorry, the dynamic speed is in R3. So this pseudo, let's say, is supposed to give more accurate and reliable results in the GW calculation, also because we can really go high in energy without having a spurious effect, what we call ghost states. Okay, so this is also the reason why for GW calculation, I would recommend to use the pseudopotentials provided by the pseudo-dojo project, available at this URL, in which we have a pseudo for non-conserving, a PW, 3 different exchange correlation functionals. We have a pseudopotential for scalar relativistic or fully relativistic pseudopotentials with the spin-orbit coupling. And we provide 2 tables. The standard one is designed for ground state application. And in this case, for instance, you will find what I call gallium D, gallium with just the 3D electrons. It is a standard table, but we also have a stringent table that has more valence electrons, smaller core radii, that is designed for highly accurate ground state calculation or medibody, which we want to have good scattering properties in the empty region, and also semi-core states to account for this overlap in the Fock operator. And all these pseudos have been validated by computing equation of state for elemental solids and then comparing with the all electron results. And we performed some convergence study with respect to the cutoff energy. And on the basis of these convergence studies, then we provide the hints for the initial cutoff energy for the wave functions that you can use to start your convergence studies. Okay, last 2 slides related to the GW fund structure. First of all, in conic form, once you have the density, you can perform a band structure calculation along an arbitrary path. In GW, or even in RT4 hybrids, this is not possible. You cannot obtain quasi-particle energy at arbitrary k points. you can only compute corrections for the k-points that are included in the wave function file that you use to construct the Green's function. And this is a mesh, it's not a path. So you can only have finite, let's say, set of quasi-particle energies in the blue zone, and you cannot have a structure plot. If you want to have a structure plot, then you have to resort to some kind of incorporation. There are different methods. In the simplest case, you just fit the quasi-particle correction as a function of energy. This is very crude, but relatively easy to implement technique. You can use it just at the beginning to have some idea, but I would not recommend doing that. You can use a Bannier interpolation. I'm not entering into detail, but everything is explained in this article here. It's very accurate. The problem is that you rely on maximally localized Bannier function, and there are systems in which obtaining maximally localized Bannier function is not trivial. And another approach is based on the star function interpolation. I don't know if you have ever used bootstrap code, but anyway, you take advantage of some symmetry properties of the energies in K-space to perform a least square fit while preserving these symmetries. So you don't need any kind of bannerization, although you can have problems in the presence of banner crossing. But anyway, just to show you, let's say that the main idea and how to automate this the calculations. This is a Python script. These objects are implemented in AppyPy. We have an SCDF file produced by Beneath with the self-energy corrections computed for all the key points in the irreducible Brillouin zone. We read this file, okay, and then instead of interpolating the quasi-particle corrections, we interpolated instead of interpolating the quasi-particle energies, we interpolated the quasi-particle corrections, the difference between quasi-particle and that's the reason why we also read another file produced by the Konesham part. GSR stands for ground state. Once we have these two objects, so the Konesham bands and the quasi-particle energies, then we just call this function here that takes care of performing this star function interpolation. And then we just call this plot method. And here we have this figure that shows the LDA band structure and the interpolated results for the quasi-particle band energies for silicon. And I think yes, my last slide, and I thank you for the attention.
By this contour deformation technique can give satellite feature. By this contour deformation technique can provide us with these satellite features, and they are absent in the Z method.
Wait, the plasma pole method, I would say. You can define Z also in the contour deformation.
No. The method to solve the quasi-particle equation. There is a Newton expansion, Taylor expansion that you use, and then you have a Z as a weight of quasi-particle Beacon block. But you said that in contour, actually, using contour deformation technique, here you are able to capture those satellite effects as well.
Yes.
Okay, which are absent in the solution using this Taylor expansion.
Yeah, because Z and the quasi-particle energy gives you the peak. If the Z is small, since the spectral function integrates to 1, this means that the spectral weight has been already shifted. It's shifted that. So you should see some additional structure here that gives some contribution to the integral. In many cases, you have this satellite that corresponds to an interaction with other oscillation, the plasmon and interaction with the plasmon. But in order to see the satellites, you have to compute the spectral function.
Yeah.
Because when we solve the quasi-particle equation with the linearized method, essentially we are working here.
Okay, small.
Indeed, the Z gives you the area associated to the peak. It's a local description.
But once you apply contour deformation, Is it related to this that we have some residual effect or no?
What do you mean with the residual?
Once you consider this contour, you had a slide there, right? There are a few poles of, those green crosses that you will compute the frequency dependence. You have integral over image axis and contribution coming from poles inside the contour.
Yes.
So is it related to that, this satellite feature?
Oh, great question. No, he's asking whether the satellite feature is related to the
Technique that we are dealing with self-energy.
If your question is if the numerical integration of the convolution is done properly, you should see the same results independently of using deformation of brute force sampling from 0 up to infinity or analytic continuation.
So it doesn't
The
matter.
idea is to reduce the number of frequency points needed to converge the convolution as much as possible. So this is the main idea of the contour deformation. There are other codes, Berkeley GW, using Berkeley GW.
Yeah.
Berkeley GW integrates from 0 to infinity.
Yeah.
But then you have oscillations. And here, the idea is to, okay, you have oscillations, but you only need to compute the residuals in this region. Another important contribution to the integral is given by the imaginary part that is much easier to converge.
Yeah.
And again, as I mentioned, these residuals are limited in frequency. There's a certain omega max, beyond which you don't have contributions. So this means that you don't have to sample from 0 to infinity.
Yeah.
You can stop, I don't know, here in the calculation of the probability. So usually this requires less frequencies than a brute force integration. But if the two methods are converged, then you should get the same spectral function.
Do you use a uniform sampling of the frequencies or some algorithm?
Along the imaginary axis, there is a Gaussian chart. And along the real axis is a linear mesh. Because indeed you have a cutoff here, and then the number of points you want to sample.
I have a question also about the quasi-particle wave functions. So we saw how we can calculate the quasi-particle energies, but how do we calculate the quasi-particle wave function?
I should have a couple of slides. This is related to the so-called quasi-particle self-consistency. Because you can have one shot EW, then energy only, that is perhaps the simplest kind of self-consistency we want to try, in which you just update the eigenvalues. Then you decide if you want to update in W only, in G, in the self-energy. If you say, suppose that the quasi-particle wave functions differ from Cornish-Sham, then you should do some kind of self-consistency in which you have to diagonalize the self-energy. Because the self-energy is not going to be diagonal, this Cornish-Sham representation. That's the reason why I was saying that the off-diagonal matrix elements are needed if you want to go beyond one shot. For one shot, you just compute the diagonal terms. And, okay. Let me remember what we were here. Okay. Now, the problem is that self-energy is not Hermitian. So if you try to diagonalize it, there are a lot of numerical instabilities. So that's the reason why people started to suggest approaches in which you construct a static and Hermitian approximation to the self-energy. Kind of effective Hamiltonian in terms of the GW self-energy. And in this paper here, for instance, they compute self-energy and then take the off-diagonal matrix elements between the two Cornish-Sham states. Then you have to deal with the frequency dependence. So that is that you compute that epsilon I, epsilon j, and you take the average. And this allows you to define an effective Hamiltonian. okay? And then you diagonalize this operator. This allows you to compute new quasi-particle wave functions, so you have a new density, new R3, and then you iterate again. And this new wave function, in principle, is used to recompute the lemma representation, the new polarizabilities. And yeah, let me remember from this paper. Yeah, so you know, one shot tends to overestimate the experimental values. Because of consistency, you overshoot, but it improves. The problem is that it's more expensive than one shot. But then there are also other effects related to the gap. We have been working also on electron phonon interaction. But anyway, I don't want to bother you with those. Thank you.
What types of vertex corrections can you apply? Vertex corrections, what is implemented in the ability?
So we have a vertex correction in W, but DDFT, like.
The same that Francesco already introduced, so a kind of best W tilde, which include a vertex but in a TDFT-like, so with an exchange correlation kernel of TDFT. So it's, let's say, an historical way, but I mean, it's not, so far there are no clear proof that is improving everywhere.
But we can also compute the electron phonon interaction.
Yeah.
Because I mean, you also have the interaction with phonons that tends to reduce the band gap. So since including the vertex performing some kind of self-consistency usually overshoots, our idea is that one should also include the electron phonon interaction to have these additional effects. And also because this gives you the temperature dependence.
Until you compute thermal diagrams for the phonon corrections?
Yes.
Okay.
Is there a constraint for using GW in the 2D materials or slab?
You mean what?
Is there some, can we use it in a material that has a large vacuum as a vacuum?
Yes, as you know, plane waves do not play
Yeah.
well with vacuum.
Yeah.
But yes, we also implement cutoff in the Coulomb interaction. I mean, it's very well known that you have this interaction within periodically repeated images. That's the reason why you have to converge your calculation with respect to the vacuum. And it's true in Kohn-Sham. It's even worse in GW because you have no local operators that are more sensitive, to this interaction. So the idea is essentially to cut the Coulomb term. If you have a two-dimensional material, you want to have an interaction that is untruncated along X and Y, but you cut it along Z. And so we have different cutoff techniques that you can use at the GW level. Again, it's just to accelerate the convergence with respect to the vacuum. Okay. Yes. Okay.
Here for that zinc oxide, that zinc sulfide, you're missing vertex corrections for sigma.
This is a GW electron. Is a calculation in which, yes, they include the vertex in W with VASP. This calculation comes from VASP, and then we normalize it by including the correction due to the electron phonon. Okay. As you can see, essentially, the electron phonon interaction allows one to decrease the gap and bring it in better agreement with the experiment. And this calculation are even more demanding than GW, the electron phonon.
You are talking about this GWEH?
Yeah, GWH.
GWH is electron hole or?
Electron hole in the, yeah, it means a vertex correction in W to account for electron hole interaction. And then on top of this GW electron hole, then we take into account the electron phonon self-energy. Because GW is only, well, in its equation are formulated at clamp ions. And then when you have to go beyond to take into account that ions are moving, then you have 0 point acceleration and temperature effects, because these temperature effects when you start to populate phonons, not electrons. But as long as your gap is larger than KT, the electronic degrees of freedom are not affected on phonons.
It seems that the zero-point motion always closes the gap, while there are two terms. The fan, the Migdal term, no? If I remember, that opposes one to the other. And so if it is one of the two, should be a positive correction to the band gap, while in so here I see always negative correction. This is on top of the square, no?
And the Migdal, the biwall,
The biwall, sorry.
they cancel the acoustic limit.
Huh?
They cancel each other in the acoustic limit.
They cancel each other.
They cancel each other in the acoustic limit.
Okay, but let's say they are opposite inside, no? So not in the acoustic limit, you should expect that
The acoustic
one
limit, they
can
must be
be
opposite because they cancel each other. For other frequencies, why? It's clear to me that they cancel well. They must have opposite canceling the
If
acoustic
they
limit.
cancel each other, then you should not have a correction to the zero motion, to the gap. Zero
No.
correction. If they cancel perfectly. Okay.
In the acoustic limit,
Okay.
they cancel.
But then they are opposite. And so in one case, it could be that the biwaller is larger than the fan Migdal. There can be also a case that it's the other way on. So, yeah. Then it's a question I always ask it to people doing this electron phonon calculation. And they told me, no, there should be some system in which you have an opening of the gap. But so far I have not seen.
No, you can have it.
You can have it.
The majority when it tends to shrink, that system in which you have this opening, phosphorus.